Well, in previous videos, we talked about actuators and specifically about electric motors. And when we were talking about electric motors, at the end, we said that there was a controller, usually a microprocessor or microcontroller, that was in charge of controlling the motor. Okay? Well, to achieve that, the controller sends a signal to the motor. The signals can be different, but it is usually employed what is called pulse width modulation. In pulse width modulation, the controller uses a signal that is kind as a square signal, with part of it being high value and part of it being low value or null value. And depending on the proportion of, um, of the high value regarding to the low or null value, the whole signal is considered stronger or weaker. So, and that's usually the signal the engines or the motors receive. But what I'm more interested in speaking about is about control. And we will apply here what is called the classical theory of control, but we do not only employ here in robotics, but almost in every automation or every control problem. So let's say when we will had a controller sending a signal to the engine, to the motor, we are operating in what is what is called, sorry, the open loop. And so you send the signal, cross fingers, and hope everything goes right. And that finally the engine arrives at the position or the speed or the power you're looking for. But that's not what really happens usually in real life, because every error there could be in your calculus, any misconception in your model, or any unexpected effect on the environment makes that you don't uh, achieve the position or the speed you're looking for. So usually in the theory of control, we apply what is called closed loop control. In closed loop control, you are not just applying a signal to the engine or whatever, but what you really do is you're measuring the output and compare that with your objective, with the output you really expect. And so the controller really acts on the error, the difference between what you want to achieve and what's the real output. And the controllers usually have three components. First component is the proportional component or P component. The P component just applies a constant, let's say a constant to the error. So the signal you send to the engine is proportional to the error. And usually this proportional component makes you reach your goal or try to reach your goal quickly, but usually cannot prevent an error, an steady state error. The second component is the integrative component, the I component, and it applies really an integral. As you may remember, an integral is kind of summing up, in this case, error. So really what the controller is acting on is the cumulative error. And the integral component allows us to eliminate that steady state error, but tends to exaggerate correction, and due to inertia phenomena, it's not strange that it exceeds the desired value, although in the future time they arrive at the desired value. And so we need the third component, the D component or derivative component. Derivative component uses derivatives that, as you may remember, is kind of measuring change. So to a certain extent, the derivative component anticipates the future, and so allow us to avoid overreaction, but on the contrary, make the the system more sensitive to noise. So not every single component is good, but usually the common controllers combine the three components, the proportional P, the integrative I, and the derivative D, giving rise to what is called PID controllers. Well, this is, say, first layer of control. In robotics, we usually put another layers of control on top of this basic layer, but we will speak about these additional layers of control in future videos.